I'm sorry for that delay. You want me to just...
Yeah, I just want to adjust it. Okay. 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 So good morning, everyone. So today we're going to finish. It's 8:04 right now, so we're going to finish 8:54. Okay. This is the example that we did last time. We had to design a column. Okay. We were given the dimensions, and we were required to find the area steel. So we assumed that phi is equal to 0.65. Okay. So we solved that example till the end last time. There was only one thing that we need to do. What's that? Check if phi is 0.65 as we assumed or not. How to check this? How to check if phi is 0.65 as we assumed or not?
To make sure that it's in between 1 and max.
Exactly. So this is the point that we got, which is in that range from here to here, so that means that phi is 0.65. If your point was below that one line, okay, this one Fs divided by F yield equal to 1, if the point was below that line, then phi is not 0.65 as you assumed. As long as the point that you get on the curve is above that line, you're good, okay? Your assumption is correct, okay? So that's one last check, okay, here. And then you have to design for the stirrups, check the spacing between the bars, and so on, as you did exactly in chapter 9, okay? Now let's go ahead and solve another example here. So that's example 10.4. So right now, we're going to solve few examples. We already solved example 10.3, okay? And then there will be another 2 examples on the design of beam columns, or columns under combined axial and bending moment, okay? What are the 3 examples? Exactly the same as we did in beams. When you design a beam, what were the 3 options for the problem for me to give to you for a design? You remember in chapter 4?
Dimensions on area steel.
Okay, so yeah. So there were 3 things. We already covered one of them in example 10.3. I gave you the dimensions, and I require you to find area steel. This is what we did in example 10.3. Okay, I give you you have 2 unknowns: the dimensions and the steel, right? In the previous example 10.3, I gave you the dimensions, and I'm requiring you to find the area steel. The other alternative for me to give you as a problem is I don't give you anything, the dimensions or the area steel. Do you remember in chapter 4, if I don't give you anything, what would you do? Yeah, or if I don't force any dimensions to you, so use some, you don't check it back again, just get some dimensions according to some like guidelines, right? You assume the depth of the beam equal to the span divided by 10, and then the width is equal to 1/2 that value, right? And then now you have the dimensions, you design for the area steel, right? That's what we're going to do now in example 10.4. You have nothing, so you're going to have to assume or find some, dimensions, okay? And then find area steel according to what we did in example 10.3. So in this example 10.4, we have a P ultimate that is equal to 600 K, and we have an M ultimate that is equal to 80 Gibbs feet. And we're required to design a short square column with steel distributed over the 4 faces of the column. Fc prime is equal to 4 ksi F field is 60 KSI. So this is similar to the example that we solved, but in the previous example, you had the dimensions, okay? So now, to solve this example, I don't want to use the word assume. I would say find the dimensions, okay? But they are not based on any equation. Just find some dimensions, okay? I don't want to use the word assume, because, I tell you, when you assume something, you have to check it. Here, no, just use those dimensions, okay? Just assume those dimensions and use them. There is nothing to check about them, okay? So here, we're going to find some dimensions, area gross, okay, of the column, just equal to the compression force, P ultimate, divided by some average stress of 0.6 FC prime. Okay? This is not an equation. Why 0.6 FC prime? I have just a number, okay? I can use 0.5 FC prime. I'm just getting some initial dimensions, okay? And then the area steel will complete my design to fulfill that this column really can resist those loads, okay? This equation is just, something out of the blue, okay? It doesn't have any mathematical or any scientific background, just an assumption, okay? So P ultimate is 600K divided by 0.6 FC prime is 4 KSI. So here I would design my column to have 250 inches square, okay? This is a squared column, so try 16 by 16 inches by 16 inches. That would give me an area gross of 256 inches square. Okay? So now my column is squared column. It's 16 inches by 16 inches. Now, after doing this step, I just have what I had in example 10.3, okay? There is nothing new that I'm going to do over here, okay? The steel is distributed among the four faces of the column, so that means that you have to use the interaction diagrams that adhere to this one. You have to assume a cover distance, so this is 16 inches. The cover over here, I'm assuming 2.5 on that side, so that's 11 inches over here, okay? Now to design this column, to find the area steel, you just need to use the interaction diagram. To use the interaction diagram, you remember the interaction diagram is a relationship between the normalized Pn, which is Pn divided by Fc prime area gross, and here you have Mn divided by Fc prime area gross H. Okay? So we call this term Kn, and this one is Rn. So I need to find Kn and Rn. So Kn and Rn are function of Pn and Mn, not P ultimate and M ultimate. So I need to find Pn and Rn. So how much is Pn? Pn is P ultimate divided by phi. Do you know how much is phi? No. Again, we're going to assume. Okay? So we're going to assume here, this is a real assumption that we have to check. Okay? Assume phi equals 0.65. P ultimate was 600K divided by 0.65. So that is equal to 923.1K. This is P ultimate, and this is P nominal. So P ultimate is 923. M ultimate is M nominal divided by phi.
You're right, I forgot. It's P nominal.
P
Nominal equals P ultimate over P.
P nominal. So
That's what you need to put in the equation.
P.
Nominal is multiplied by P.
Okay. P ultimate is.
It's It's phenomenal.
Yeah, yeah.
No,
Yeah, sorry. P nominal is P ultimate divided by phi. And here, this is M nominal is M ultimate. M ultimate, how much was M ultimate? 9? 80 Gibbs feet. 80 Gibbs feet divided by phi, okay? So I don't have that number over here. Divided by 0.65. Let me see here. 80 divided by 0.65. 123.07 Gibbs feet. So now I can go ahead and find Kn. Kn is P nominal divided by Fc prime area gross. P nominal is 923.1 K divided by Fc prime, which is 4 KSI. Area gross is 256 inches squared. So that is equal to 0.901. What's the units of Kn? Unitless. Okay. Rn is M nominal divided by Fc prime area gross H. So M nominal is 123.07 Gibbs feet divided by Fc prime, which is 4 KSI. Area gross is 256 inches squared. H is 16 inches. Are the units consistent here? Yeah, so I have to multiply here by 12 inches per foot to have every dimension in inch. Okay? So Rn is going to be 0.0901. What's the units? It's unitless. Okay? It's normalized moment. Okay? Normalized Pn. Okay? So now you need to go and use the interaction diagram. You have a set of interaction diagrams. Yes? What's what? This 0.0901. So now for the interaction diagrams, you have 12 interaction diagrams. 4 for the columns where the steel only on one face, 4 for the steel distributed over the 4 faces, and 4 for circular columns. Okay? So we're going to be using the 4 interaction diagrams where the steel is distributed among the 4 faces. Which of the 4 interaction diagrams you have different gammas? Gamma 0.6, 0.7, 0.8, 0.9 at the back of your book. So which gamma? So here I need to go ahead and calculate gamma. So gamma is this 11 inches divided by the 16 inches. So 11 divided by 16. So gamma is 0.6875. Okay? So you have to use the figure for 0.6 and you have to use that for 0.7 and interpolate the two values. Okay? So over here, this is, just to show you this is example 10.4. So this is for gamma equals 0.9. Pn was 0.9 something, right? Rn was 0.09, so over here. So that's the point that you're looking for. How much is rho? For this point, you're looking for rho. Here, rho is 0.02. Here, it's 0.03. So you interpolate in between, so it's 0.025. Okay? Maybe 0.024. A little bit less than 0.025. Okay? This is for what? This is for gamma equals 0.6. Okay? You repeat the same thing for gamma equals 0.7. This is the figure for gamma equals 0.7. Again, here Kn is 0.9. Here 0.09. You get this point. It's 0.022. Okay? So those are the two values. Okay? And then you interpolate the two values. Okay? So interpolating, it's going to be 0.0235. Find rho for gamma equals 0.6 and 0.7 and interpolate. So interpolating, we're going to find that rho required is 0.0235. So therefore the area steel required is rho required. It's not BD, it's multiplied by the area gross over here. So 0.0235 multiplied by 16 inch. So you need 5.89 inches squared. You would say use number 8 bars, right? You have to have the steel distributed among the 4 faces over here. So you need 3, 6, you need 8. Okay? So 6 number 9. So instead of using 6 number 9, we're going to use 8 number 8 bars, which is equal to 6.28 inches squared. And then check the, the distance between the bars, design the stirrups, and so on. So any question regarding this example? How to use the interaction diagrams? Okay? So again, this example is exactly the same as example 10.3. The only difference is we added one step at the beginning. In example 10.3, we had the dimensions. Here, I had to assume some dimensions because I didn't have any dimensions. Okay? So just assume rough dimensions, and then the area steel required is the one that will fulfill your, design to resist the given P ultimate and M ultimate. Okay? Any question here? Okay, great. The next example, what do you think the next example will be covering? What's the third case for design? Not area steel, row. Right? I'll give you a row, and you're required to adhere to this row and find dimensions that is adhering to that percentage of steel. Right?
So in that case, we don't have to use the interaction diagram to find rows.
We're going to see. I'll show you how to solve this. So example 10.5. So here we have a round spiral column to be used to support P ultimate of 500K and M ultimate of 225 kips feet. So those are the loads applied on the column. Okay. FC prime is equal to 4 KSI. F yield is equal to 60 KSI. Oh, no, not this one. I'm sorry. This is example 10.5, but I'm not going to solve example 10.5. I'm going to solve example 10.6. Okay? Example 10.5 is similar to example 10.5 is similar to 10.4, but it's for circular. So here in example 10.6, we're required to design a 14-inch wide rectangular short tied column to support a P ultimate that is equal to 500K, and M ultimate that is equal to 250 kips feet. So those are the loads, okay? Steel is placed on two faces of the column. Use rho that is approximately equal to 2%. FC prime is equal to 4 KSI, and F yield is equal to 60 KSI. So here you need to design for the other dimension of the column, okay? You have a column that looks like this. The width over here is 14 inches. You have steel on both faces, only two faces here. And how much is that distance H? That's what we want to find. The area steel, we don't know how much is the area steel, but we know rho should be about 2%. Okay? So you need to use the interaction diagrams. The only thing that you have is the interaction diagram. Okay? So how to use the interaction diagram? To use the interaction diagram, you need to know Kn and Rn, which are function of the dimensions. Kn is Pn divided by Fc prime area gross, right? So without knowing the dimensions, I won't be able to use the interaction diagram. So here, I'm gonna do it the other way around, okay? I'm gonna assume a dimension and find rho, okay? I'm gonna assume an H over here. Once I know H, I can use the interaction diagram. What will I get from the interaction diagram? I will get rho, but rho is given, okay? I will get rho, okay? If the rho that I get is 2%, so that dimension that I assumed is correct, okay? What if I don't get 2%? Assume another dimension till I get 2%. That's what we're gonna do. Okay? Is it clear? So here, we're gonna assume an H. So H, okay? If H is 20 inches, okay? If H is 20 inches, you have the dimensions, okay? You can go ahead and find Kn. What's Kn? It's Pn divided by Fc prime area gross. Pn is what? Pn is P ultimate divided by phi, right? Area gross is what? Area gross is the 14 inches multiplied by H. Fc prime is given, it's 4 KSI. P ultimate is given, it's 500K. So you just substitute the value of H over here, you find Kn. So Kn would be 0.687. You find Rn according to the assumed value of H, okay? So Rn would be, how much is Rn? It's M nominal, which is M ultimate divided by phi, Fc prime, area gross, which is 14 multiplied by H, so that's H squared. M ultimate has to be in kips inch, so just change it to kips inch, so the value that you have here just multiplied by 12. Okay? So find Rn. Rn would be equal to 0.206. Now I have Kn and Rn. I go to the table, okay? Still need to find gamma, okay? How much is gamma? According to the, the distance that you have here, the cover, okay? Assume a cover of 2.5 inches. from here and 2.5 inches from here. So gamma here is going to be 15 divided by 20, so it's 0.75. That means that you're going to need to interpolate. Okay? Gamma here is h minus 5 inches divided by h. Right? So that's gamma, so I can go ahead and find rho. Rho is going to be interpolated for 0.7 and 0.8. Rho, doing this, rho is 0.0315. Is that the rho that we're looking for? We wanted rho to be equal to 2%. We had 3%. So what would you do to decrease rho?
Increase h.
Increase h, okay? Make the dimensions larger, so rho becomes less, okay? So I'm going to assume here h equal to 24 inches. If it's 24 inches, Kn is going to be 0.572, Rn is 0.143, gamma is 0.792, and rho is 1.1%. Is that what you're looking for? No, you want 2%. So what would you do? 22 inches. If you have 22 inches, this is going to be 0.624. Rn is going to be 0.17, 0.773. Interpolating the two values for rho, you're going to get exactly 2%. So it's a trial and error, okay? You assume an h, okay, and see if you get the required rho or not. If you get the required rho, great. If not, go ahead and repeat that again and again until you get the required rho. So therefore, use h equal to 22 inches, okay, and find the area steel. It's equal to rho multiplied by BH. Rho is 2% multiplied by B, which is 14 inches, multiplied by H, which is 22 inches, and conclude your design. Any question? Any question? Okay, so let's go ahead and move to example 10.7. Yes? So here we're assuming an h and find rho till you find h that gives rho equal to 2%. That's what we did. Okay? We assumed an h, we find rho 3%, we assume 24, we got 1%, we assume 22, we got what we're looking for, 2%, so that's the h required. Yes?
Would there be a case where we would get really close, but not exactly?
Yeah, definitely. Like for example here, let's say you assume 22, you got 0.0202. I would say that's what I'm looking for.
Could you go to half inches to get closer? Or?
No, the dimensions of the column has to be rounded to the nearest inch at least, not the, usually it's even number, okay? But at least a full inch, okay? But practically, it's a even number, so 20, 22, 24, and so on. Yes?
Is that supposed to be 22, 22, or is that going to be 2.5?
I cannot hear you.
On the bottom equation,
Yes.
102 times 14.
Yeah, that's 22. Okay? So, any question? So now those three examples, okay, covers the design of a beam column using the interaction diagrams. Is there any other option for a design or the statement for a design problem? We just covered everything. I didn't give you anything, the dimensions or the steel. I gave you the dimensions and I required you to find the steel. I gave you the row and I required you to find the dimensions. Okay? So those are the three problem statements that you could face. Okay? Nothing else. So example 10.7, okay, we had example 10.5, okay, or 6, okay. Now example 10.7 is not about a design, okay? It's about analysis. So what's the analysis? What is meant by analysis? Okay, so an analysis problem is you're given the dimensions, right? And you're required to find P ultimate and M ultimate, the capacity, the strength of that column, right? We already did this. When did we do this? No, in chapter 10. The interaction diagram, okay, is the strength of a beam column, right? The interaction diagram, what's the interaction diagram? You have a column with a given dimensions, a given steel, right? That's the second example that we solved, right? And we plotted different points. What are those points? Those points are the strength of that column, right? So what about example 10.7? We're saying it's about the analysis, okay? It's about the analysis, okay? You're given a column dimensions, okay? Everything about the column. And you're required to find just one point on that curve, okay? Here you have Pn normalized and Mn normalized, okay? And I'm asking you to find what's the strength of that column. That's what we're going to do in this example. The strength of that column. So that the eccentricity is given. I give you the eccentricity. What's the eccentricity? The eccentricity is Mn divided by Pn, right? That's the eccentricity. So you have many points here on that curve. Each point has a different eccentricity. What's the eccentricity here? Zero. What's the eccentricity here? Infinity, right? The eccentricity is Mn divided by Pn. Pn here is 0, so the number divided by 0 is infinity. So every point on this curve, as you go from here to here, you change from 0 to infinity. So 0, 0.1, 0.2, 1, 2, 3, and so on till you reach infinity. Okay? I want you to find one point on that curve. Okay? I will give you an eccentricity. Okay? I want you to find what's the strength for that given eccentricity. Okay? So that's what we want to do. Why do I care, or why would I give you an eccentricity? Okay? Because if you have a frame or a structure, okay, like this, and you apply a load, one, let's say, on the structure, okay? Let's say you have a frame like this, and you have a uniform load over here. Wn. It will give you some normal force and some moment in the column here. If this Wn is doubled, it will give you a normal, the normal force will get doubled, the bending moment will get doubled. But the eccentricity, will it get doubled? No, the eccentricity will remain the same. Why? Because the eccentricity is Mn divided by Pn. So the eccentricity is constant, regardless of how much that will change. As long as it's the same distribution, okay, the same load, if the value of the load just changed, doubles or triples, the eccentricity is the same, right? The eccentricity is Mn divided by Pn. If Wn doubles, both of those numbers will double, the eccentricity will remain the same, right? So that's why I care about the eccentricity, okay? because it's a constant here. Whether this load is 100 or 1,000, the eccentricity is the same number. Okay? So here, that's the example that we want to solve. We're required to determine the value of Pn for a short, tight column if the eccentricity in the x direction is 10 inches. Fc prime is 4 ksi and F yield is 60 ksi. The column that we want to analyze and find its strength looks like this. We have 3 number 10 on this side and 3 number 10 on this side. So width over here is 12 inches and the dimensions on this side we have 3 inches, 3 inches and 14 inches, so overall that's 20 inches. So if I have a column like this, okay, you have an Mn and Pn, and the eccentricity over here is 10 inches. That's the eccentricity, okay? How much is Pn? The maximum Pn, okay, that can be supported by that column if the eccentricity is 10 inches, okay? So you just have the interaction diagram, you just need to find one point, okay, where the eccentricity is 10 inches, okay? So let's go ahead here and see what do we have on this interaction diagram. You have interaction diagrams at the back of your book, you're going to use them, okay? The normalized interaction diagrams at the back of the book gives you Kn, which is Pn divided by Fc prime area gross. On the horizontal axis, you have Mn divided by Fc prime area gross H. What's Mn? Mn, and it's given in using this notation at the back of the book, Pne. Mn is Pn multiplied by the eccentricity E. Okay? So let's go ahead here. And here you have those interaction diagrams for different rows. Okay? Let's see here. If you divide Rn by Kn, what do you have? Rn is Pn E divided by area gross Fc prime H divided by Kn, so that's the inverse here, Fc prime area gross divided by Pn. Okay? So actually this and this can cancel with this and this Pn can cancel with this Pn. So dividing those two values, you're going to have E over H. Right? E over H. That's the division of the two values here. Rn divided by K. Right? That's the kind of the slope, right, of some line, right? Rn divided by Kn. So if I have this E, how much is the eccentricity here? 10 inches. How much is H? It's 20 inches, right? H over here is 20 inches. So this is 0.5. So the point that I'm looking for as an Rn divided by Kn equals 0.5. Can you draw a line where Rn divided by Kn equals 0.5? How to do this? Just come here, okay? draw a point here. This is 0.5. This is 1. This point here, for this point, Rn divided by Kn is 0.5, right? Any point on that line Rn divided by Kn will be 0.5, right? Right or not? If Rn divided by Kn for this point is 0.5, any point on that line, it's a straight line. So it's the same slope. Now, how much is rho for that column? Rho is given. It's an analysis problem. Rho is the area steel divided by area gross. Area steel divided by the area gross. How much is the area steel? The area steel was 6 number 10, which gives you an area of I guess, let's see here, 7.68 inches squared divided by area gross, which is 12 inches by 20 inches. So rho is 0.0316. So if this is rho here, 0.03, here 0.04, the curve that I'm looking for by interpolation is somewhere over here. So for this curve, rho is 0.03. The intersection here is the point that you're looking for. This is your interaction diagram for the given rho, and that's the point over here is where you have an eccentricity of 10 inches. Okay? You just need to, which curve are you using here? You need to use the curve with a gamma. You have many curves. Which gamma? Gamma over here is 14 divided by 20 inches. That 14 divided by 20. So that's 0.7. So in the curve with gamma 0.7, you're just going to draw this line and draw this line and find the intersection. That's the point that you're looking for. For that point, how much is Pn? How much is that dimension? This is Pn divided by Fc prime area gross. Right? From this, you can solve for Pn. Right? You measure this dimension, and then you multiply by Fc prime area gross, you find Pn that you were looking for. So that's the strength of that column. Okay? So Pn, from here, Pn is going to be equal to 460.8 K. Any question? Okay, so thank you a lot, and see you on Wednesday for the exam. It's going to be here from 8 to 10. Okay?
Are you going to post the homework with solutions?
I already posted the homework. Yeah, but not the solutions. The solutions are in the book. If you don't get the same answers as in the book, just...
Will you be on campus tomorrow?
Yes. I'll be on campus till 12. I guess. We have a lunch. I don't remember the time. And then I have a meeting in the military science building over here. So maybe just a lunch. So, yeah.
And on the test, how many problems can we like?
Most probably 4.
Well, like one from each. 8, 9, and 10, and then one.
8, 9, and 10. Maybe 10. You're gonna have 2 problems on 10.
The one we didn't homework.
You have the homework, right?
No way.
Shear. You have the shear, the columns, and beam columns on the test.